So I thought what I would do, since this is sort of a whole day devoted to the bootstrap, is start with a basic introduction to the conformal bootstrap. And then hopefully I will have time after that introduction to talk about some of the recent developments. And in particular, I want to focus on the applications to three-dimensional quantum field theories. So I'm going to I'll call this overview of parenthesis 3D bootstrap. And maybe I should just say a few words about why we're doing this whole thing to begin with. So why are we interested in learning about conformal field theories? So for me, there's a few reasons. One is that they're the basic building blocks of quantum field theory. In the sense of almost every quantum field theory can be thought of as a renormalization group flow from a CFT in the UV to a CFT in the IR. Sometimes this IR, if your theory has a mass gap, this IR CFT might be completely trivial because everything decouples. But you always get some sort of scale invariance in the deep IR and scale invariance in the deep UV. If you want to understand strongly coupled quantum field theory in general, this is a good place to start.
Could I actually already?
Please do.
No, you said almost every quantum field theory can be understood as flows between fixed points. And what's the basis for that? I mean, I certainly know, we know of some counterexamples, like little string theories look like non-local quantum field theories. They're also in 3D. I guess there are these long-range Ising models that flow to conformal fixed points, but they're not kind of what we call them. They don't have
I never said the word local anymore.
Yeah, you didn't say local, but it's not clear what that is there a UV?
So there are some theories where we don't know how to flow to them, or if we flow away from them, where they go. So that's completely true. So we don't understand this in general. So
and of course you can have free field theories like 5 to the 4 in 4 dimensions.
Yes.
Where the CFTs, there's no CFT in the UV. So it's a trivial theory.
It's I would call it trivial theory. I would say a trivial theory has conformal symmetry.
Okay. No, but is there UV fixed point though? If it's 5-4 theory in 4 dimensions?
If it's trivial, it doesn't flow at all, so it is a fixed point. I think that's what you said.
Yeah.
No, I think the fixed point at the zero coupling is a UV fixed point.
This is a
it's an IR fixed point. It's not a UV fixed point.
This is a
and it doesn't come from
UV complete continuum
that's
quantum
right.
field theory.
Yeah, it's a UV complete.
Yes.
So you can also have things start
no lambda
lattices, and you can
absolutely.
Not,
and I think there are also exceptions to this when you go into the realm of non-relativistic field theory. And anyway, so let me put a. Many examples fall into this category. So another reason is the ADS-CFT correspondence. If you believe the ADS-CFT correspondence in generality, then studying CFTs is a very good way to learn about how to put together consistent theories of quantum gravity and ADS. Okay, so from my perspective, one motivation for learning about CFTs and doing the bootstrap is to really learn about quantum gravity. So that's one reason. From a more, if you like, practical perspective, lots and lots of real-world condensed matter and statistical systems are described by conformal field theories. Okay, so these are all systems that, when adjusted to second-order phase transitions, these are systems in both 2 dimensions and 3 dimensions. And so one example that I will make many references to later is the 3-dimensional Ising model. And so there are lots of systems which are described by the 3-dimensional Ising CFT. Just to give one example, if you look at fluids, 3-dimensional real-world fluids, and look at their temperature, pressure, phase diagram, then there are lines separating the liquid, solid, and gas phases. And the line separating the liquid phase from the gas phase ends at a critical point. And we believe that in lots and lots of different fluids, the physics at this critical point is the same, it's universal, and it's described by the 3D Ising CFT. Okay, so there are lots of real-world systems that we're trying to learn about when we do this endeavor as well. Okay, if you're an optimist, you could also hope that physics beyond the standard model might be described by conformal dynamics. We don't have any evidence for this yet, but there are lots of interesting ideas out there. And so learning about CFTs is important if we want to see if any of these ideas work. Okay, so from my perspective, these are the main motivations for what we're doing.
I'm just curious, at the tricritical point or whatever, the cross you drew down there.
Yes.
So why is it the Ising CD then rather, how do you think is the Ising model then and rather than any other 3D CFT? Is there a reason to think it should be modeled by the Ising spins like a 1 bit per point?
Good. So, you know, in some ways this is an experimental observation. Okay, people measure the critical exponents describing the physics at this point, and they're identical to the critical exponents that you see in, say, magnetic systems, which are in the Ising universality class.
But do you have any hand-waving understanding of why they should be?
Yeah. So I mean, so one understanding is that it has the right symmetry, the right global symmetry. Namely, there's
just a Z2.
A Z2 symmetry and nothing else.
Yeah. And what is the Z2 in this situation, in the physical situation? Is it between the liquid and the gas?
So in principle, you look at a Potts model too, like, I mean, other than Z2, like if you would have a system which is complicated enough to do that.
Yeah, absolutely. There are lots of systems out there.
But is there any obvious Z2 in a liquid gas transition? Or which Z2 is it?
Yeah. So in this situation, the role of the scalar field is played by fluctuations of the fluid density.
Okay. Yes,
away
yes.
from some critical value. And there's a Z2 symmetry which takes that to minus itself.
Okay, so overdense and underdense, that's
Yeah.
Z2 symmetry. Okay.
That's right. Okay, good. Any more questions about before I even get to the bootstrap?
And
Okay.
And you can roll the boards if you.
Oh, I can roll the boards. Let's do that. All right. Okay. So what is a CFT? Let's start there. So from the perspective of the bootstrap, a CFT is a quantum field theory with an extra symmetry. Okay. It's an SOD, 2 or SOD plus 1, 1 symmetry, depending on whether you're in Lorentzian or Euclidean signature. So this is the conformal group. It contains the usual translation generator, rotation generators of the Poincare group. In addition, it has a generator of scale transformations and what's sometimes called a special conformal generator, which generates shear transformations which preserve angles. And so this is the conformal group. It has these 2 extra guys. okay, you can start, organizing operators in terms of their quantum numbers under all these generators. So we start looking at local operators. And okay, in general, they can be labeled by their scaling dimension, delta, and their spin quantum numbers, their eigenvalue under the action of mu nu. Okay, so this is the dimension. These are the Lorentz representation. And okay, for a traceless symmetric tensor, this would be an integer which is labeling the spin. Okay, so in addition to this, we can divide the local operators into two other categories. One is what you would call primary operators, and the other is what you'd call descendants. Primary operators are the ones that are killed by the special conformal generator. Okay, and descendants are what you get when you act on a primary by p, the translation generator. Okay, so something like p dot p O, which is the same thing as taking derivatives of the operator schematically. Okay, so this is basic story with local operators. Let me also mention that in unitary conformal field theories, there are constraints on the scaling dimensions of operators. These are ultimately coming from the requirement that 2-point correlation functions are positive. Okay, in particular, 2-point functions of descendant operators have to be positive, or the states that correspond to them in radial quantization have positive norm. And so unitarity gives you lower bounds on the scaling dimensions of operators, which in general are that the dimension is greater than or equal to d minus 2 over 2 for scalar operators, and it's greater than d plus L minus 2 for spin L operators. Yeah.
For the applications to statistical and mechanical systems and the Euclidean dimensions,
yes,
unitarity is not.
It's not a requirement. That's right. Yeah. So if you're in Euclidean signature, then people usually call this reflection positivity. And there are lots of interesting systems that are reflection positive, so you can use these requirements. So the 3D, the Ising model is an example. But there are also non-reflection positive systems as well.
In that context, I should think of this as kind of an extra symmetry. Is that a right way of saying it? On constraint on the conformal field theory?
Yeah, It's an extra constraint on the conformal field theory. I don't know if I would call it a symmetry, but it's not a symmetry in the same sense of SOD comma 2, but it's an extra element of structure that the theory can have.
Do you want to divide that by 2, the second one?
What's that?
Do you want to divide the second equation?
I do not divide the second equation by 2.
So for L equal to 0, you don't get the scalar case out.
That's correct. That's right. This is only for L bigger than 0. Yep. Okay, good. Okay, so now we can.
Just one more question.
Yeah.
So is the unitarity bound always the dimension of the you know, the free field at that spin. Like d minus 2 by 2 is the dimension of a free scalar.
Yes.
In the dimension.
Yes.
So it's
Yeah.
always that?
Well, this
I don't
is
know.
the bound in any dimension, so yeah, that's right.
It's saturated
It's-
if and only
Yeah,
if
that's what I'm
it's
saying. Is
it's
it always
free.
saturated?
It's saturated
by the
if
free
and
field?
only if it's free.
Okay.
Yeah, that's right.
Your
Um,
question was for non-scale.
Even for spin
And-
L,
and for
I mean,
spin
I can
L,
see
then
for
these
d
are-
equal to 2, it's okay. I think.
These are the dimensions of currents in
Yeah.
right, conserved currents. And for L, you know, larger values of L, these are higher spin currents. So if this bound is saturated, then the operator necessarily satisfies a conservation condition. That's the analogous statement.
Okay.
Yeah. Good. More questions?
So just wait a moment. If I take d equal to 4
Yes.
and L equal to half, I get the right answer?
Oh, sorry. So this, I'm just writing down the answer for integer.
Oh, for integer.
Integer spin.
I see.
Yeah. Yeah. They're
Okay.
also formulas you can write down.
Oh,
for
so that's why you said these are
right.
currents.
Okay, integer. That's right.
I'm still a little puzzled. What kind of algebra would give me an answer which works for all L but not for L equal to 0? The answer changes. What calculation has a jump in it?
So the calculation is, you know, here I start with a scalar primary operator, and start looking at its descendants.
Right.
Okay, so there are lots of different descendants I can look at, and I calculate their 2-point functions, and see what requirements are in place,
Right.
so that they're all positive,
Okay.
and then I can also do this for spin operators with
Yes,
spin.
so I was just asking just a
And-
very simple hand-waving reason why the answer for other L wouldn't work for L equal to 0.
I guess all the
But
higher
it's-
spins are some currents. The spin 0 is not a current.
The guy that has zero
Yeah.
norm is at a different level. Right?
Yeah.
For the scalar, it's
the-
a level
the
2.
guy- that's right.
And all in,
That's
the
right.
other guy's at
Yeah,
level
these
1.
these constraints all come from
Kind of a one derivative.
level 1 descendants acting with one
Okay.
1p. And there there are things you can do like contract the derivative with the index on the spin L operator that you can't do in the case of a scalar.
You can contract the spin with
Contract the derivative with an
Okay, so that's
index
the
on the
big
spin
thing.
L operator.
So that's the difference.
Uh-huh.
So that's one, yeah. And here, as Chris said, the constraint is coming from level 2 descendants, so two p's acting on the operator. So, yeah. Okay. Okay, so now we can ask what this symmetry tells us about the physical observables in the CFD. So in particular, what does it imply for correlation functions of local primary operators? And okay, so it tells you that the 1-point functions necessarily vanish by conformal symmetry. There's no scale which could appear on the right-hand side to make an object like this have the right symmetry properties. It tells you that 2-point functions are also completely determined by conformal symmetry. Okay, so in this case, there's some tensor structure in the numerator, and the denominator this is notation for x1 minus x2 to the 2 times the dimension of O power. Okay, so this form is completely fixed in terms of these are Lorentz indices, the spin, and the dimension of the operator. A similar thing happens when you start looking at 3-point functions. So here, let me look at 3-point functions between two scalar operators and, say, a spin L operator. This is, again, completely fixed by conformal symmetry. Okay, there's some numerator, and the denominator is fixed in terms of dimensions and spins of the operators. Up to an overall coefficient. So I'll write as lambda phi phi.
Why phi? What's the difference between phi and O?
So here I'm specializing to the case where these are scalar operators, and this is, say, a spin L operator.
And also just when you make the ij depend on x1, 2,
Yes.
in principle the denominator doesn't mean anything unless I guess you specify.
Sorry, I was just not writing this out explicitly. So for example, this guy, if I have say this is a spin 1 operator, okay, but there's one index, then this guy is the metric minus
This is some standard.
it's just some fixed function like this. Yeah. And same for these guys in the numerator. Okay, so yeah, so here, as you noticed, I was specializing to the case of 2 scalars and 1 operator with spin. Of course, you can look at 3 operators of arbitrary Lorentz representations. And in general, what you find is that you can have multiple tensor structures which are allowed. And each of those structures comes with some unknown coefficient. Okay? So in general, there's a finite number of tensor structures. And you can work them out. An efficient way to, sometimes it starts getting pretty complicated if this is spin 7, spin 5, spin 20, right? It gets complicated to try to write down all the different tensor structures. An efficient way to work them out is to work in an embedding space formalism, where the idea is that you can work in a higher dimensional space where the action of the conformal group is linearly realized. And because it's linearly realized, it's much easier to analyze which structures have conformal symmetry and which don't. So that's in practice, that's the best way to start getting a real handle on this situation. Okay, but I'll focus on this simpler case for now and come back to this later if there's time. So knowing all these 3-point functions is equivalent to knowing the form of the operator product expansion. Okay, so this is equivalent to knowing the operator product expansion. So in particular, if I take phi of x1 times phi of x2, then this has an expansion over which runs sum which runs over all of the operators in the phi OPE. The coefficients in this expansion are the same as the 3-point function coefficients. And okay, there's some function of coordinates and derivatives which acts on local operators at one of the points.
These are primary operators? Or?
Yeah, this is a sum over primary operators. And so what this function is doing is that saying if I know how a primary operator appears, then this function tells me how all of its descendants appear. That's what this derivative dependence on here is. And this function is completely, it's completely fixed by conformal symmetry in terms of the dimensions of the operators. Okay, so right now the only things in the game are the dimensions and Lorentz representations of the local operators and the coefficients appearing in the 3-point functions. Those are the only numbers that show up in the OPE. And once you have the OPE, you can use it to start evaluating higher point functions, like 4-point functions. And so in principle, every other correlation function is fixed in terms of this set of data.
Sorry, so CI is also fixed by these considerations, or is CI also some standard thing like I that you didn't write? But
Yeah, that's right. The problem is this guy's a bit of a mess. You can look up a formula for it in the paper by Dolan and Osborne. But
it doesn't
it's
require computation so much. It doesn't require model-dependent computation.
That's correct. Yeah, the only thing it depends on are the dimensions of the operators. But otherwise, it's completely fixed by conformal symmetry.
Are you assuming that we're working on flat Euclidean or Lorentz space here? Or?
I'm assuming we're working in flat Euclidean or Lorentz space.
Okay.
That's
so
right.
This wouldn't determine all correlators on a curved background. If we knew it on flat space, we need some additional data.
That's right. So you could ask if there's data that we're missing by only thinking about correlation functions of local operators. So there might be non-local observables, which you would need to know in order to put the theory on a curved background.
Okay.
So I'm not talking about that. Philip, you look puzzled.
Yeah, I'm just, why going to a curved background means you have to look at non-local operators? I understand that there could be all sorts of, in addition to the local operators, there may be non-local operators,
Yeah.
even in a flat space. Can't you say that there's, so I don't understand it in either direction. In the flat space, aren't there also things that may not be determined just by knowing all your local endpoint functions, namely correlation functions of Wilson line
Wilson
operators
lines,
and stuff
yeah,
like that, which aren't decomposable into products?
They could appear on the right-hand side of that OPE.
No.
They can't appear on the right-hand side.
The mean value of OX doesn't have to be 0 for a curved background.
That's right. So I'm in a flat background here.
Yeah. But I'm also curious at the other thing. Why do you say when going to a curved background that you automatically have to? I mean, I would have just thought there's some.
Well, so all I'm really saying is that if you only know the local observables, then you might not know how to put your theory on a curved background.
I guess
Okay.
if you have like closed cycles, you could have non-local things particular to that might be one thing.
Exactly. So that's an example. Yeah, if your background has some cycles in it, then you need to know how to talk about operators which wrap around those cycles. Non-local operators.
What if I don't add any crazy topology? I just have put in some little bumps in my geometry.
Yes. Then you might be okay.
Is this enough local information to somehow?
Yeah, if you just put little bumps into your geometry, I think you just need the stress tensor.
Yeah, you
because
generate
that
those.
Yeah,
Yeah.
split the deformation with
Right.
some local operators.
So that's putting, I see,
Yeah.
you put in some kind of
Yeah,
coherent
it's
state with the stress tensor.
okay. Maybe I should. Yeah, maybe we should go on. But these are good. Questions. Here. Okay, so I just told you that if you know this OPE, you can start evaluating higher point functions. And so the main thing we're going to look at are 4-point functions. And the simplest version is to look at 4-point functions of scalars. So here I have scalar operators at 4 different points. I can evaluate this function using the OPE. Well, first of all, before I do that, you can ask, what does conformal symmetry tell me about the form of this function? And if you work through it carefully, what it tells you is that this function depends on up to an overall factor which depends on the scaling dimension. This guy can be anything which is a function of the 2 conformally invariant cross ratios that you can build out of 4 points. Okay, so here u is x12 squared, x34 squared, over x13 squared, x24 squared. This is invariant under any conformal transformation. And v is the same thing, but with 1 and 3 switched. Okay, so just by conformal symmetry, this could be some arbitrary function. But now we can evaluate what this function is using the OPE. So if I bring these 2 points together and these 2 points together, graphically, you could write it like this, where I have intermediate operators showing up in the OPE, which run in this line. And this is a graphical representation of, so I have my prefactor. I have a sum of my OPE coefficients squared, because I've done the OPE twice. And really, if I plug in the OPE, what I get are these differential operators C acting on 2-point functions of O. And those give you objects which are functions of the 2 cross ratios labeled by the dimension and spin of the operator appearing in this sum, which are called conformal blocks. Okay, so these guys fight, and again, O is a primary operator. So what these guys do are they sum up the contributions of all descendants of a given primary to the 4-point function.
David?
Yeah.
Is it conceivable that this operator product expansion doesn't converge?
Excellent question.
I know in 2 dimensions it doesn't happen. But
Good. So you should, no, this is a great question to ask. So when does the OPE converge? So the answer is basically the OPE will converge if it can be interpreted as a change of basis in radial quantization. So another way to say it is, let's say I have my 4 points, which are somewhere, and if I can draw some ball around 2 of the points, and the other points are outside of this ball, then I can interpret the OPE between this operator and this operator as a change of basis in radial quantization. Okay, and then the OPE converges.
That's if or if and only if.
What's that?
If or if and only if.
Oh,
are there
well,
theories known where it doesn't converge?
No. So if this is true, then it definitely converges.
Okay, yeah.
I don't know if there are situations where it magically converges even if you're outside of this.
How about the other way
regime.
around? Are there theories known for which OPE doesn't converge? Some concrete model, is it known or?
No,
So
not so.
that this condition fails? isn't true?
No, I don't know. I mean, I write down some Hamiltonian, calculate OPEs of that
So
operator.
in general quantum field theory, the OPE is an asymptotic series.
Right.
But here we're in the realm of conformal field theories where you can make a rigorous argument.
Yeah, that's what I
for
meant.
convergence.
So, I mean, if I go to the conformal point, I mean, do we
Yeah.
know of any examples where this doesn't?
No,
So this
no,
doesn't
no.
happen, basically.
And furthermore, in the 4-point function, you can basically almost for every configuration of the 4 points, draw a circle like that. So it basically converges almost everywhere in the
I see.
as a function of the 4.
Right. So the trickier thing will be in a second. We'll start doing the OPE in multiple ways, and then what you need is for it to converge in all different ways of doing the OPE. If you want to write down a bootstrap condition that makes sense, and that does place a non-trivial restriction on where you can be in U and V space. So I'll get there in just a second. So this gives us an expansion in conformal blocks. As I just said, this was only one way of doing the expansion. You can also, say, bring these points together. And so, for example, if you write down the equation that this sum is equal to this sum, these are both sums, then you get a non-trivial constraint. Another way to think about it is we started with an object which is invariant under permutations of the different coordinates, and that permutation symmetry is not manifest when you write the correlator in this form. So for example, I want to demand that this is invariant under exchanging x1 with x3. That exchanges u with v, and so I get a non-trivial constraint. So we can just write that down very concretely. Sum over OPE coefficients squared of g of u and v equals, so there's some prefactor coming from these terms that you can work out, that being u over v to the delta phi power, times a sum over OPE coefficient squared times g of v and du. Okay, so this is one of the simplest bootstrap constraints, conformal bootstrap constraints. You should view it as the only free parameters in this equation are the OPE coefficients and the dimensions and spins of the operators appearing in these sums. And otherwise, these conformal blocks are special functions which are completely determined in terms of the dimensions and spins. And so this is one of the equations that the bootstrap would be trying to analyze.
There are other inequivalent equations that give more information? Or does this generate everything?
Good. So you get more information by, here I only focused on 4-point functions containing a single scalar. So if you put different operators into this
Still, I
function.
just mean the equivalence of the crossed graph.
Yes.
That's all you ever use in Bootstrap.
Well, there's another channel.
That's right. So in this case, the other channel doesn't give you new information.
Right, there's a T channel.
Yeah,
U
so
channel,
there's
right.
S equals T equals U, but in this case, you don't get new information from the U channel. Really, the reason is that that's say equivalent.
Interchanging like 3 and 4.
Yeah, to exchanging 3 and 4 or 1 and 2. That exchange has just a very simple effect, which is that it tells you that only operators of even spin can appear in the sum. Okay, you can see that directly from the 3-point functions. Exchanging 1 with 2 in the 3-point functions forces only even spin operators to appear. So that does give you a constraint, but it's very easy to implement. And this is really the non-trivial one.
So may I ask a question about
Yeah.
the reality of the lambda?
Yes. Good.
OP coefficients, and why you wrote that as a square?
Well, let's see.
No,
So
why it's instead phi phi o as opposed to lambda phi phi o times lambda o phi phi. In other words, what's the relation among
good.
different orders?
So here I just did the OPE choice, and each of those picks up lambda phi phi o. Right. So there are no.
Mm-hmm.
So in that order.
Right.
Okay. So that's why I wrote it as lambda phi phi o squared. Now. So now you should ask is lambda phi phi o squared a positive number? And so the answer is that if you're in a unitary theory, you can work in a basis of operators where the 3-point function coefficients are real.
These particular 3-point function coefficients, or all?
You can work in a basis where all of them are real. Yeah. And so if you're in a unitary theory, you're guaranteed that these are positive numbers. If you're in a non-unitary theory, the 3-point function coefficients might be imaginary, and then these could be negative.
Is it equivalent to saying that beta functions, if I perturb the theory, the beta functions have to be real?
Is that equivalent to saying that if I perturb the theory?
The OPE coefficient gets related to the quadratic term of the beta function. Or maybe that's not always valid.
Well, probably, yeah. If you're doing conformal perturbation theory,
That's right.
and you try to express the beta functions in terms of the CFT data, then it might follow from doing that. Okay. So this is a constraint that we'll call crossing symmetry. And it's a constraint on the spectrum of the dilatation operator, dimensions and spins, and the 3-point function coefficients. Okay.
While you're erasing, what if you had one of these graphs with a loop in it? Is that would that give another type of constraint? Saying put a loop in and say that graph with the loop is equivalent to the one with the loop flattened out with the loop removed. Is that a new kind of constraint?
I'm not sure how to make sense of a graph with a loop. Really, it's shorthand for using the OPE.
Right. Right. Use it at each of the vertices.
When you collapse 2 to 1, you can expand it.
Yeah.
It's not a finite diagram.
No, but there would be three operators coming in at each vertex, so there's an OPE at each vertex.
But you specify
You're saying
external
so
objects.
you can take 3 operators going into 1 operator. But that's
No,
contained
that's
in
the same.
here because there's a successive steps of OPEs.
Right. So it's true if you're going to higher point functions, then you can start having multiple OPEs and the diagrams get more complicated.
But
I don't think you can have loops though.
But I don't think you can have. I don't think you can have loops.
Okay.
how about if you have closed cycles in the spatial geometry? Put it on a torus. Maybe is there a modular in there?
Yeah.
Whether this one's already.
Yeah.
It's not out there yet.
Okay, so that was sort of the simplest crossing symmetry constraint from a 4-point function of a single scalar field. So in general, you have constraints from every 4-point function in your theory. Okay, so if I have different 4-point functions with different Lorentz quantum numbers, you set S equals T equals U, and you get some very non-trivial constraint on the operators of the OPE. So this is really what the conformal bootstrap is about. It basically aims to use these constraints to hopefully solve theories, or at a minimum constrain what they can do. Okay. Solve or constrain theories. And really the most, okay, so one of the interesting things that's come out of this is that there's a real tension between these constraints of crossing symmetry and the constraints imposed by unitarity. And so that's what a lot of the studies recently have been exploring.
What do you mean by tension?
I mean that putting these two conditions together leads to strong constraints on the space of operator dimensions. Okay, whereas just having one of them on its own would not lead to that kind of strong constraint. So we'll try to see that more explicitly.
And here the constraint of unitarity are both constraints on delta as well as things like reality of
That's right.
OPEs.
Yeah, here unitarity, yeah, for me unitarity is that lambda phi O squared is positive, and the dimensions are greater than the unitarity bounds. Exactly. Okay, so you want to understand what these constraints are telling you. Of course, you can try to tackle it in various ways. You can try to study the constraints analytically, or you can try to study the constraints numerically. There's been progress on both fronts, though all of the analytical studies have been in situations where you have some expansion parameter. Okay, so you can, for example, do analytical studies of the crossing equation in large N theories where you have a 1/n expansion parameter. You can also get analytical results which constrain the spectrum of CFTs at large spin, and there you can do an expansion in 1 over the spin to make an analytical bootstrap argument. But away from those kinds of situations, making analytical arguments is pretty hard. And so most of the really exciting results have been numerical, in more than 2 dimensions. There have been, I should say, there were a lot of exciting results from the bootstrap in 2-dimensional CFTs. So here I'm mainly talking about more than 2 dimensions.
Sorry to ask, I should know this from paying attention, but in 2 dimension, the results are new, or are you referring to something from like 80s and 70s?
Oh, I was referring to papers from the 80s.
Okay.
Yeah. That's right. Though I guess we will hear about some new results in 2D CFTs.
I should have been paying attention.
Very soon. Yeah.
So another expansion parameter is if you have a conformal manifold.
Yes.
Have people found any relations? I mean, if you know you have a solution of crossing symmetry at one point, can it say something about?
That's a really good question, and I would like to know the answer, but I don't think anyone's really gotten a nice result along those lines yet. So let's see. So I should say something about what the conformal blocks are, and then I'll try to mention how you get numerical results from the bootstrap, and then show you some of the more recent results. So let me first say a little bit about the conformal blocks. Because if you want to study this either numerically or analytically, you need to know what they are. So one simple way to understand what they are is that they are eigenfunctions of the Casimir operator of the conformal group. Conformal Casimir, which means that they satisfy a nice second-order differential equation. And so you can try to use that differential equation to solve for the conformal blocks. And so this approach has actually led to some very nice closed-form solutions for the conformal blocks in even space-time dimensions. Closed-form solutions in B equals 2, 4, 6, dot. So this is these are some nice results by Dolan and Osborne. Okay, these solutions can be written in terms of hypergeometric functions, 2f1 hypergeometric functions. So even space-time dimensions are relatively easy to deal with. More generally, in particular in 3 dimensions, which is what I wanted to say something about, we don't know nice closed-form expressions for the conformal blocks. Okay, so no closed form.
What's the difference between even and odd dimension? Why? Why can't you get?
Well, it's harder to solve the differential equation. So this is a very analogous situation to solving the wave equation, and solutions to the wave equation in even dimensions versus odd dimensions look different. I mean, solutions in even dimensions satisfy Huygens principle, where they look like a superposition of incoming and outgoing spherical waves, whereas that's not true in odd dimensions. And so I think there's something analogous to that going on here. Okay, so there's no closed form known, but one of the things that we've sort of understood how to do over the last few years is calculate them very, very precisely. And so one of the most efficient ways to calculate the blocks outside of even dimensions is to use the fact that they satisfy a nice recursion relation. And you can motivate this in the following way. So one way to think about the blocks is that, okay, so they're a sum over primary operator and all of its descendants. Okay.
Sorry, can I ask?
Yeah.
When you look at the wave equation, there is a recursion that goes the jump dimension by 2. You take the derivative and you get.
Yes.
So here you could, if you knew the 3 dimension, could you get 5? And all
Yes. Yeah. There is a recursive relation which relates blocks in d dimensions to the blocks in d+2 dimensions. absolutely. So that's one of the ways to, if you know the two-dimensional blocks, you can generate all the higher ones. Similarly, if you know the three-dimensional blocks, you can generate the 5D ones and 7D ones and so on. So absolutely, that's correct. Okay, so but what I wanted to say is that one way to think about the blocks is they correspond to a sum over all the different possible intermediate states. Where those intermediate states run over the primary and all of its descendants. But these intermediate states are also normalized. And this way of thinking about the blocks, one thing it shows you is that if your operator has any descendant which is a null state, then this should blow up. Okay, so this is actually reflected in the structure of the blocks, namely, as a function of the scaling dimension, the blocks have a series of poles in them, where those poles correspond to dimensions of operators which have descendants which are null states. And let's see.
But if you have a null state, why does the 5-5 couple to it? Should it not couple to it?
So these well, phi. Well, here we're talking about phi coupling to a primary operator O, right? Where O has a descendant, which is a null state.
No, I was just confused because if you have a unitary theory, can't you write it with a set of states which
Good.
have
So
null
all of
states?
these dimensions that I'm talking about here are non-unitary. Okay, so they can't be realized in unitary.
Right now we're not talking about unitary theories, you see.
That's right. Here, right now I'm talking about the general structure of the blocks, which as a function of the dimension, and I can imagine taking that dimension to non-unitary values. But this is actually a very useful thing, because what it does is it tells you that you can write the blocks as some function which I'll call G infinity plus a sum over poles. And the basic point is that if you have a descendant which is a null state, then it and all of its descendants form their own sub-representation of the conformal group. They only transform into each other under conformal transformations. And so that means the residue of this pole is itself proportional to a conformal block. Okay, so this leads to an expression for the blocks where you can make all of these poles very, very explicit. And then this guy sitting out in front is a known function that you can, for example, solve using the Casimir equation at very large values of delta. So this ends up being a very useful recursion relation for the block. Namely, I can take this expression, start plugging it into itself, plug it into itself, plug it into itself. Each time I do this, I get a more and more accurate approximation to the conformal block. And so this is what we're doing in practice, to actually calculate these 3D blocks. So this is a recursion
So this is a tool which at the end can help you get the blocks even for the unit group theory.
That's right. That's right. All these poles occur at non-unitary dimensions, but this is a correct expression for delta unitary. That's right.
So this in some sense is like an expansion for large delta. Is that the idea? And it, is that the right way of thinking about it? And
so
delta above the position of all the poles.
That's right. I mean, this is a way of making all the delta dependence completely manifest. That's the delta dependence of this guy is very, very simple. So that's really what it's doing. There's no delta in here anymore, right? These are all the deltas. So the other nice thing about this expression is it makes it clear that there's a sense in which the blocks can be thought of as rational functions in delta. Okay. Now these are namely I can write this as some polynomial numerator over a polynomial denominator, which is going to be very useful for the numerical applications later. So I'll mention that in a second.
Is that a finite sum on the right-hand side?
This is an infinite sum on the right-hand side, so they're infinite order polynomials. But you can truncate this sum and get a very, very precise approximation to the block. That's basically the point.
So it converges exponentially rapidly?
It converges. Right. So actually, this is nicest when the blocks are written in terms of radial coordinates. Radial coordinates are you can take your 4 points and put them in a configuration where 2 of the points are symmetric around the origin, and the other 2 points are at 1 and -1. So I can do this with a conformal transformation, and then the location of this guy is rho, and the location of this guy is minus rho. And so like rho equals r e to the I theta, and this is the radial coordinate that I'm talking about. So the nice thing about radial coordinates, so each time I plug this recursion relation into myself, it increases the order in R. And the nice thing is that if you go to the crossing symmetric configuration, then that corresponds to R being around 0.17. So an expansion in R converges very quickly. Okay, so this is the basic reason. Yeah.
So these G's are eigenfunctions of SOD, 2 in some sense.
Yes.
So if I write them in that fashion, these poles are signifying what? There's a generalized spherical harmonics in that case, or a big sphere. So these poles would correspond to what in that way of thinking?
I'm not sure. Of course, if I write down the Casimir as a differential operator, it acts in the coordinates, right? So these guys are functions of u and v, or r and eta, and so the differential equation starts mixing up all these terms with each other. So I'm not sure if there's an easy
So I'm just confused. If you want to do spherical harmonics of SOD, 2,
yeah.
I thought people would know all the spherical harmonics for all spins for all SODs. I mean, oh, that's not true. Don't we already know the answers in that language?
Well, this isn't. It's not quite the same thing. So first of all, this is a non-compact group.
Yes.
and so that's
That's part of the problem.
that's part of the
People
issue.
sometimes stick in eyes here and there to
Yeah.
get from, usual SODs, spherical harmonics
Yeah.
and these things, but they give you all kind of bad functions.
Yeah.
So it's because you have these continuous series and so on, you
Yeah.
have a problem.
That's right.
Yeah. So there
that's
there
good
isn't an
for-
easy way to
good
get to the
for
answer knowing the SO equals
SO3, that's SO2 comma, even for SO2 comma 1, that's a problem.
Yes.
Okay. So I just wanted to show you this because
Got it.
Yeah,
all right,
yeah.
we better go. So this allows for an efficient computation of the blocks, and it also makes manifest that there are nice rational function. A nice way to represent the blocks in terms of rational functions in the dimension. So those are the two points. So now let me move on to trying to tackle bootstrap numerically. So the basic strategy is to make some assumption about the spectrum entering your crossing relation, and then try to prove that crossing symmetry cannot be satisfied subject to that assumption. So make an assumption. One simple kind of assumption is that all scalar dimensions are greater than some minimum dimension. And then the concrete strategy is to then apply a functional alpha to the crossing relation. A functional which takes a function of the two cross ratios to a real number. And so if I write my crossing relation in the form of a sum rule, okay, so it's a sum over OPE coefficients squared by O times some function of cross ratios. And here I've separated out the identity operator contribution in the OPE. This guy is just, I should just write it. This guy is just V to the delta phi times the conformal block minus U to the delta phi times G. Here's G of U and V, here's G of V and U. So this is just a way of rewriting the crossing relation I wrote before. So now I can apply a functional to this equation, which takes a function of two variables to a real number. So I get 0 equals alpha f of 1 plus a sum over lambda squared times alpha f delta L delta phi. And then I look for a functional which implies a contradiction. So one simple way to do that is to try to find an alpha such that, let's say alpha of f of 1 is positive, and all of these other guys are greater than or equal to 0. Okay, so if this is true, this is strictly positive, these are greater than or equal to 0, then they can't possibly sum to 0. So then what happens? This leads to a contradiction. And you rule out whatever assumption about the spectrum that you made.
Could you say again what the word applying a functional to crossing relation meant? I think I blanked out on that one.
Well, so right now it's completely general. It should be a linear functional. In practice, what this is going to be is taking derivatives, linear combinations of derivatives of the crossing relation at some point.
So you start with, crossing relationship means knowing G, right?
What's that?
Or the crossing relation is not G. What?
So
that is the crossing, that first line without the alphas.
Yeah, this is the crossing relation.
It's
I just rewrote it in a slightly funny way.
I see. And then you say, if you do a small, it's some kind of a stability with respect to small change type argument is what the alpha deformation is supposed to be doing. I guess
So here's another way to say it. Let me take this equation, Taylor expand it around some point in UV space. Okay? And I Taylor expand to some finite order, so I get some set of equations, which are the coefficients of that Taylor expansion. Then I look for linear combinations of those equations which lead to a contradiction. That's basically it.
Okay.
and where does the assumption lead in?
Yeah, so this assumption shows up down here on which functions I impose this constraint on. Okay, so in this case, I would impose this constraint only for scalar dimensions greater than this minimum dimension. And you can you can make this more complicated. You can say, I assume the first scalar operator is at 2.3, and then the next one starts at 4.7, and then I'm ignorant about the spectrum above there, and you can impose that in your set of constraints. Okay, so that's.
But can I ask?
Yeah.
So I mean, maybe there are other ways, but like in this case, like you don't have to make an assumption of the whole spectrum, right? Because like you can just throw off any delta now that's a constraint on a single conformal block. Right?
Sorry. So
not the sum of it.
Yeah. Sorry. So if this constraint is
Oh, I see.
true
Sorry.
for all delta bigger than delta min,
Okay.
then it doesn't matter what the rest of the spectrum is.
Yeah.
That's part of the point, is that we can be completely ignorant about what the spectrum looks like, and still rule out.
It's hard to
this
kind of
assumption.
keep asking the same
Yep.
point, but basically the only conceptual input is that crossing relation. You're checking to see if crossing relation is intrinsically consistent.
And we're using the fact that these coefficients are positive.
Okay, you use the positive. And then you say you do Taylor expansion. What do you say Taylor expansion in? So you're kind of taking the equation and breaking
In U and V.
In U and V.
around some point.
Yeah. So let me just make it more explicit.
I see. So just a linear combination of expansion U and V implies the positivity that you just covered. That's what.
Right. So in practice, what people do is take this functional to be some linear combination with coefficients of derivatives. Usually it's in terms of variables z and z bar, which are z bar. These kinds of coordinates, but that's not so important. Evaluated at some particular point. In this case, 1/2, 1/2. So when I say look for a functional which satisfies these inequalities, I mean scan over all these possible coefficients and see if you can find any set of coefficients which leads to this contradiction.
And I mean, because
Yeah.
the conformal block are not known analytically, right? So do you have control on? Because here, you have control on how much you don't know about. Because the function that you're acting upon
Yes.
with the functional is not known analytically, right?
That's right. So I just told you before this that we We can compute it
Okay, as precisely.
as precisely as we want.
Okay.
Basically, by applying this recursion relation over and over and
So
over
that
again.
means as many Taylor coefficients as you need, you're saying? Is that what?
As many,
Or?
right, I mean, so there's still an approximation, right? So we're only going to some fixed order in this expansion in radial coordinates, which implies some error.
So that's
But
that's my question.
yeah.
You have control on the error.
But we have control over the error.
So
We
so long
can-
as so you can make sure that.
Yeah.
Yeah. Okay.
Yeah, we can always, go to higher order and check if the
you know,
results
it doesn't become
change.
negative. or
Exactly.
But it's just a clever way of extracting information from the fact that you have a lot of information for the fact you have infinite choice of U and G
Yes.
to play with. So this is just a organization principle.
This is an organization principle. That's right. And there are different, there are other ways you could do this. I could evaluate U and V at lots of different points. I could do some funny integral in U and V space.
Just that this one happens to be computationally efficient.
This one happens to be computationally efficient and successful.
But you said that these points have to be chosen so such that both expansions converge.
That's right.
Then you cannot like integrate or.
Well, you'd have to only integrate over the region where both expansions converge. Yeah. Okay, I'm worried that I'm running out of time before I get to any of the results. But okay, so let me finish this discussion and then I'll try to do some summary of the results. Okay, so one thing that is sort of clear from this recursion relation for the blocks is that if I look at derivatives of this function, then all the delta dependence can be made explicit, and you can check that this takes the form of some positive function times a polynomial in delta. Okay, so the statement that linear combinations of these derivatives are positive is equivalent to the statement that linear combinations of polynomials are positive. And so what we really have here is some optimization problem with polynomial constraints, or we can phrase it in this language. And this is the kind of problem that can be solved using methods that are called semi-definite programming. Namely, the constraint that a polynomial is positive can be rephrased as a constraint in terms of positive semi-definite matrices that represent the polynomial. And then this becomes an optimization problem involving positive semi-definite matrices, and this is a sort of form of convex optimization which is well studied. So in practice, right now, this is what we're using.
What is a positive semi-definite matrix?
It's a matrix with all positive eigenvalues. Greater eigenvalues all greater than or equal to 0.
Why is semi? That's not positive definite.
No,
They
it's
can be zero.
non-negative.
Yeah, non-negative. They could be equal to 0.
They could equal to 0. Okay, that's what it was.
That's what the semi means. Yeah.
So non-negative.
Yeah. All the eigenvalues are non-negative. Okay, so in practice, we're phrasing this problem in this language right now, and we have been using a semi-definite programming solver called SDPA, and it has a sort of high-precision version called SDPA GMP. This is the GNU multi-precision library. And so most of the studies that have used this approach have used this so far. More recently, my collaborator David Simmons-Duffin wrote his own semi-definite programming solver, which I will now advertise, which is sort of optimized for these kinds of problems and roughly 10 to 100 times more efficient at solving the problems. So this is going to come out in the near future and be publicly available. So if anyone wants to get involved in the bootstrap, you should be on the lookout for this. Okay, so let me, in the last 10 minutes, take a little more time. Okay, let me mention some of the results that have come out of this approach. So this is all in 3 dimensions. And okay, so one very nice result has been placing bounds on the first scalar operator showing up in the OPE. So here, this is what I was calling delta phi. This is the first scalar in the OPE, which you could call delta phi squared. And you can rigorously rule out some region of this space. Okay, so this whole region is disallowed. Here, the axis is 1/2, which is the dimension of a free scalar, and 1. So a free scalar theory sits right here in this corner, and you get some excluded region. So the interesting thing about this is that it has some structure to it, and there's some sort of funny kink here, and this occurs at 0.518, 1.41, which we believe are the scaling dimensions in the 3D Ising.
Do you need to imply that these lines are actually straight, or is it sort of approximately?
It's they're not exactly straight.
So all you can say is there's a kink there.
Well, that's right. You know, there's that you can fit them by straight lines, and it's not too bad.
But I was just curious if people in the field are claiming it's a straight line.
No.
Okay, just
no.
But the kink is a real kink. It's not a smooth thing which is approximately looking
if you at some finite numerical precision, if you zoom in on this enough, it'll be smoothed out. But it's pretty sharp.
But that's a numerical accuracy issue, not. I mean, the question is.
Yes.
I guess so implied by this question is
yes.
That part is ruled out. Is
yes.
the area just inside that ruled in? At least is there expectation that it's ruled in such that the line is the line indicating the state of art or physics? I guess that's the question that I'm asking.
Right. I think it's unlikely that this whole line is populated by CFTs.
Well, I'm actually speaking of entire region inside.
Yes.
But you say it's unlikely. So you're likely that you're going to kill more, and what's left over, whatever method, but whatever left over is a very small islands and droplets.
That's right.
Okay.
That's right.
It may be populated by 4-point functions.
Right. This is
right.
Being populated by CFTs.
That's right. So here we only looked at a single 4-point function.
What do you mean by populated by 4-point functions?
There might be 4-point
yeah.
function solutions to the cross-link symmetry relation, even though
yeah.
there's
there might be solutions to the single 4-point function crossing relation
yeah.
along this line, but not to the full system.
I see. So if you start
function
imposing the
crossing
other constraints that you haven't looked at yet,
that's right.
You expect to whack much
that's right.
more of this.
And if I have time, I'll give you an example of that.
Right.
Yes. Okay, so this is one of the exciting results. Really what we get are some sequence of curves depending on how many derivatives we include in this functional. Okay, so you start with some curve like this, you increase the number of derivatives, and you get a stronger and stronger bound. And at this point, it's pretty well converged. Okay, so this is one nice result. You can also do things.
Significance that this point is on a kink?
Well, that's a very good question. Is there a significance? I'm sure there's a significance to it. So
I guess what is the significance?
Oh, well, that's a different question.
I'm sorry.
So this is a very important question, I think, and we have been trying to understand the answer to it. And so one way we've been trying to understand the answer to it is by not just bounding this dimension, but trying to reconstruct the solution to crossing symmetry along this line and seeing what happens as you go through the kink. So we have some picture of that. And so the basic answer that we've gotten from that, going through that exercise, is that to the left of the kink, you have an extra low dimension scalar operator in the spectrum as compared to the right of the kink. Namely, that's right. So if you look at more of the spectrum, and I can tell you how we got this, but you know, so here the first operator, this is delta phi. Okay, these are all these scalars in the spectrum. So we get some curve for this operator. This curve is now very compressed. But then you look at the next operators, and what happens is you have two lines here which actually come together right at this kink point. And then become one line. So we see some picture like this.
Oh, I see.
So there is some sort of sharp transition in operator dimension space, we think. But understanding the best way to characterize what's going on here is still, I think, an open question.
Is something happening to three-point functions?
So, right. So I think one way to interpret this is that one of these operators is decoupling from the spectrum as you approach this point. And this is something which you might interpret. You could try to interpret in various ways. So it's similar to the fact that in 2 dimensions you have, in the 2D Ising model, you have states which decouple, null states, because you have degenerate representations of the Virasoro symmetry. It's also, you know, similar to if I'm in weakly coupled theory in 4 dimensions, you have some equation of motion, which you know, so an equation of motion in phi to the 4th theory tells me del squared phi is phi cubed. So an equation of motion tells me that some operator, which I naively expect to be there, is actually a descendant. So it's not part of the primary spectrum. So thinking about the implications of equations of motion, or the analog of the fact that you have degenerate representations in 2 dimensions, is how we're trying to understand this. But it's not a completely clear picture yet. Okay, so let me say you can also, okay, so one of the other things we've done, so you can also bound other quantities, not just the first scalar. You can bound OPE coefficients. You can bound the central charge of your theory. So where the central charge is defined as the coefficient appearing in the 2-point function of the stress energy tensor. And so we also can get a picture. You end up with a lower bound on the central charge, where the central charge, this is C over C free for a free scalar. This is 1. And so another thing that's happening at this point is that the central charge seems to take a minimum value. So that's another interesting thing about the 3D Ising solution, is that its central charge seems to be lower than that of the free theory, and it's probably the 3D CFT with the lowest central charge that exists. That's a conjecture. So this is something that we called C minimization. Because minimizing the central charge is a nice way to try to get at this point.
So what's the value?
Oh, the value is it's like 0.9465. So it's not too much below 1. Okay, so that's one thing.
And in this case, the curves, you were saying you come with higher derivatives and you approach it, so you approach it from below.
And you approach it from below. That's right.
And how many derivatives you go up to
when
you say you use different curves?
Yeah, so I guess in these plots, we capped the, you have derivatives in z and z bar, and we're taking up to 18 derivatives in each of those. So it's a pretty large.
Can you try to do like finite scaling, like to extrapolate to the infinite number of derivatives?
You can try that. Chris might tell you something about this approach in his talk.
I love doing that. But I don't think anyone has made a good argument for whether you should believe what comes out of you.
Right. But so you can try to do that. I mean, the nice thing about these is that at each step in this process, you have a rigorous bound, whereas the extrapolation introduces some guessing into the game. But that's right. So.
But how does it look? C as a function of number of derivatives looks like a smooth curve, or looks.
This bound, you're asking how does it look like it's converging to that line? Is that what you're asking?
Well, I was just again just the point, but not the whole curve. But,
yeah. I mean, I could look at it, but the curve. Something like this, and then it gets lower, and once we get to this point with maximum of 18 derivatives, it's very well converged to, I forget the 4th or 5th decimal place. Okay, so let me, since I don't have too much time left, let me mention a couple of the things we're doing now. So one thing that we have also done is extended this whole story to theories with certain global symmetries. So we've extended to say theories with an ON global symmetry, where we can try to make comparisons with the sequence of ON vector models in 3 dimensions. And actually we got there's a very similar story to what we have here for theories with ON global symmetry. Namely, you bound the first ON singlet scalar. So here we're looking at some ON vector across some ON vector, which gives you the identity operator, it gives you ON singlets, it gives you ON symmetric tensors, and so on. So you can place a bound on the first singlet using the same methods, and you get some sequence of curves that look like this. Where, okay, these are different values of n. So here, this was our Ising curve. This is n equals 2, n equals 3, n equals 4, ... And then you can ask, what do we know about the operator dimensions in the ON vector models? And for at least for the first few values of n, we know them pretty precisely. And so they seem to sit in these curves up to some known errors. Okay, so there are very, very accurate results from both lattice simulations and particularly in the case of the O2 model, experimental measurements in helium-4.
And did you mean to make the horizontal error bigger on purpose? Like, is that something you intended to draw, or?
So the errors get bigger as you go.
But the horizontal one is bigger, it seems. In
Both directions get bigger.
So you didn't mean to.
further up. What's that?
When you first drew it, it looked like you're amplifying the horizontal error, and I was wondering.
I should have also amplified the vertical. Let's see, the other thing I can say about this case is that in the ON vector models, at large n, you can do calculations in the 1 over n expansion. And at large n, you approach a point up here, which is 1/2 2. And so there's some sequence of points that you calculate in the 1 over n expansion. And we've checked that those 1 over n calculations match up very, very well to the locations of the kinks in these bounds. So that's one other thing we've done. More recently, the important directions that we've been pushing on are going away from the setup with a single scalar 4-point function and going to multiple systems of multiple correlators. And the other direction we've been pushing on are going to 4-point functions of operators with spin. So our current directions are mixed correlators and operators with spin. And so I should wrap up soon. Maybe
I'd say 5 minutes.
5 minutes? Great. So let me just tell you a few words about this mixed correlator case, and then I'll conclude. Because it's actually very, very exciting what we've gotten in this case. So the basic point is, if you look at something like the 3D icing model, then, okay, so far we've looked at some OPE of a single scalar operator with itself. And the 3D icing model has a Z2 symmetry, as we mentioned earlier. And so here we have only access to the operators which are Z2 even in the OPE. But we have not had any access to the operators that are Z2 odd. Now, if you want to access the Z2 odd operators, you have to look at something like sigma Z2 odd operator plus Z2 even operator. And then you get sigma plus sigma prime, dot, dot, dot.
So did you impose that as an assumption that the sigma only closed on Z, that you had a Z2 selection rule on your OPE?
No.
Well, you did not.
We did not. I mean, we sort of implicitly, when we said there was a gap in the scalar spectrum, we were ruling out the possibility that sigma appeared. But otherwise, no. But now when you go to, say, systems of correlators involving sigma and epsilon, then you can impose that kind of selection rule. And so the thing to do is to look at a system like this of 4-point functions, and you can write down all the crossing relations for this system. Write it out as a sum rule. One new feature that comes up when you do this is, for example, you have OPEs like this, which have coefficients like sigma, sigma O, epsilon, epsilon O, which are not manifestly positive. So what you have to do is sort of write the sum rule in a way that still makes some of the positivity properties manifest. And so you can write it in a form like sigma, basically in a matrix form. Where this is a 2 by 2 matrix, this is the analog of our f function in the crossing relation. And so when you impose apply a functional to this equation, you have to demand that when the functional acts on this 2x2 matrix, it gives something which is positive definite. Okay? And then that guarantees that this product itself is positive. So that can again be phrased in the language of semi-definite programming. Okay, but it's a slightly more complicated setup. So let me just say the result, then I'll be done. So when we write down this set of crossing relations and study them numerically, as I said, it gives us access to the Z2 odd spectrum. And there's actually a good reason to expect that this is important. So for example, in the Ising model, if I think about it in terms of a phi to the fourth theory, then as I said, the equation of motion, del squared phi is phi cubed. This is saying that this Z2 odd operator is a descendant. So naively, you expect some big gap between sigma and sigma prime. And actually, that's something that we see. So if I plot a bound on delta sigma prime as a function of delta sigma, where I say, let's let epsilon follow the bound curve that I put down earlier, then something very interesting happens. You get some big spike at 0.518. So right around this value is when, and this is all disallowed, is when this operator is, when you're allowed to have a big gap between sigma and sigma prime. But away from it, you can't have a big gap.
So I didn't understand the reason. So when that gap is happening, that's the time that sigma prime is a descendant.
Right. So this is an intuition from, say, the Wilson-Fisher fixed point. But so in the actual Wilson-Fisher fixed point, there is a big gap because the naive low dimension Z2 odd operator phi cubed is actually a descendant, so it doesn't show up in the primary spectrum. Yeah. So that intuition seems to be realized here. And so another way to turn this around is to say that if we impose a big gap in sigma prime, then it confines us to some very narrow window in delta sigma. So if we now go back to our sigma epsilon plane, you see that. So here was our bound that we had earlier with the kink. And you can ask, what's the allowed region if I impose a big gap in sigma prime? Say delta sigma prime is greater than 3. So we say it's irrelevant. Then what happens is you get a tiny little island, which is an allowed region. This is this small gap here. And then when you go out further, you get some other funny allowed region. Okay, so the exciting thing is now we have this tiny little solution to crossing symmetry, this tiny little allowed region which is compatible with the Ising model. And all we had to do is look at multiple correlators and put in this extra assumption. So one thing we've been doing is pushing this as far as we can go. So if I zoom in on this. So here's just a zoom in. Here is sort of the known results from Monte Carlo simulations that people have done. And by pushing this to more and more derivatives, we've been able to sort of shrink this island to be very, very much inside this region. So So we can now go, an order of magnitude more precise than the best Monte Carlo results. So I better stop there. We're currently trying to extend this picture to the ON models. And with some promising results, we're starting to get islands for the different ON models, making a comparable assumption to this. In that case, it's a gap in the ON vector channel. We're also trying to push to operators with spin. So right now we have a project trying to look at fermion 4-point functions in 3 dimensions. We've managed to understand, so you have to go through a lot of work to calculate the conformal blocks, figure out how to set up the crossing relation, and so on. But we're starting to get some results, and we can get bounds coming from fermion 4-point functions. And there's really a lot still to do. So I think all these same techniques can be applied to try to hunt down 3D gauge theories that are CFTs, which I think would be very interesting. With fermions, there's a whole sequence of gross niveau models that we want to track down. And of course, everything here can also be applied to other dimensions, like 4 dimensions. I'm hopeful that soon these bootstrap techniques can be used to find the conformal window of 4D QCD. I think that would be a very nice target for the bootstrap, and not impossible within, say a 5-year time span. So I'm very optimistic about the bootstrap. I think it's exciting, and I encourage everyone to work on it. That's it. Yeah.
As far as I recall, there was something interesting for Zn models in 3 dimensions when you cross n equal to 4. There was this one class called Potts model, the other called clock model. Maybe I'm mixing it up.
In 2 dimensions.
In 2 dimensions.
Not
so
in 3.
In 3 dimensions, I'm not aware of any Z3 or Z4 symmetric CFTs.
Okay.
But maybe if someone has an example, I'd be interested to hear it. But actually, that's an interesting direction. You can go to this multiple correlator setup, input a Z3 or Z4 symmetry, and see if you can exclude the possibility. That's a very natural thing for the bootstrap to do.
So this is a conformal window, changing like number of flavors and saying for which flavors you expect conformal.
That's right. That's right. Yeah. I'm hopeful that you input the flavor symmetry, put in some reasonable assumptions about gaps, and then you'll start seeing some sequence of islands popping out that correspond to all the different values of the number of colors. I think this is something that could happen. And something similar you could see something similar in 3D gauge theories as well.
Analogous conformal window in 2+1 gauge theory.
Yeah, exactly. Yeah, both 2+1 gauge theories and also Chern-Simons theories coupled to matter. These are both interesting targets.
So there were discussions like this with this program in 4 dimensions, right?
Yes.
And then analogous thing to your plot of delta phi and delta phi
Yes.
squared.
Yes. Yeah. So actually, this whole business started in 4 dimensions. Maybe I should have mentioned that in a nice paper by Ratazzi, Richkoff, Tony, and Vicky. And so, yeah, just because of time, I didn't go into the 4-dimensional story. But there are also nice 4-dimensional bounds. There's a lot of interesting work on 4D supersymmetric theories. Chris will tell us about some of that.
So about your like a 4 Fermi theories in 3 dimensions, have you obtained results for it? For example, one interesting thing is that like by sigma psi squared has scaling dimension 4 in 3 dimensions. Now whether you could reduce it below 3.
Yes. So we're starting to get some results. For example, I can tell you, we have some. This is the dimension of the external fermion. We can constrain the dimension of the psi squared. Yeah. This plot isn't too exciting, but it does nicely approach the free the free value.
So there are some hand-waving arguments that delta psi squared anomalous division is like half, so it's interesting to go below that. So like the 4 Fermi, a couple of 4 Fermi dimension goes from like 4 to 3, with some hand-waving argument. So I think probably this method will tell you that it will go below that.
Yeah, maybe. I mean, the other thing you can do here is you can distinguish between parity even and parity odd operators. So we're trying to explore this whole structure. And one of the theories, so one thing I can say is if you start imposing a gap in the parity odd spectrum, then this starts becoming much more interesting. So we've started getting plots which look like this after imposing a gap. And we currently have a conjecture that there's some theory which is at this lower tip, which this is like 0.5, sorry, 1.07, and this is 0.57. So these numbers are related by 1/2. And so we have a conjecture that this is a supersymmetric theory, which is the n=1 supersymmetric extension of the Ising model. So that's a conjecture that we're currently trying to develop. So I think going to fermions looks like it's going to give some interesting results. Yeah.
So when you find the island, so what's exactly the claim? So you have the deltas, but do you know more about the theory? So you say you can compute the central charge. Can you know if there are more primary operators? Can you compute the OPEs? What can you compute when you identify the island?
Yeah. So we can. I mean, this still needs to be explored more, but we can. I think we can get a similar island if you look at delta sigma versus the central charge. You'd see some small island around the central charge, and similarly for other OPE coefficients, other operators, you can start to reconstruct things that way. Also, we have a well-defined procedure if you go to the boundary of these allowed regions of reconstructing an approximate solution to crossing symmetry for every point along that boundary. So one thing we can do is reconstruct that solution everywhere around this island, and see how much the operators vary. That would give an estimate of the error, and I think we'd get a very accurate spectrum out of this procedure. Yeah.
So you get all the sum, you mean?
Yeah. So we get the second scalar and the third scalar and the higher spin operators, and we can
presumably with less and less accuracy.
With less and less accuracy, that's right. Yeah, accuracy goes down as you go up in dimension.
Well, let's thank David. Take a